Hello. Today we're going to be talking about scatter plots and lines of fit. So scatter plots tend to show a data set where things can sometimes be correlated and sometimes be not correlated. What happens is in math we like things to be perfect, so we like write equations of lines and it goes exactly through all of our points. But when we actually collect data from the real world, most of the time it doesn't show that like perfect relationship. So enter scatter plots here. So let's go ahead and take a look at the one on our screen. We have the relationship between the screen size of a TV. So notice down here the X values are your screen size, and then the cost is your Y values. So looking at these ones, a screen size that was 40 inches cost $100, but also a different one cost $300. One that had 48 inches was close to $500. So looking at this, the patterns that we might see is as our cost is going up, or as our screen size is going up, notice the cost is also going up. So the cost is increasing as the screen size is increasing. Now you also could have said other things, like you might notice that everything has a screen size of 40 or more, or everything costs $100 or more. There's a lot of different things we could notice here. So what does the set of points tell you about the relationship between the screen size and the cost of the television? Well, we're going to say that the cost of the TV is dependent on the screen size. The way we have done our variables, the screen size was your X value. Those are going to be your independent values. The cost was your Y value. Your Y values are your dependent values. So the larger the screen, the more the cost. So C is actually purely just your own opinion. How much do you think a 46 inch would cost? So think about that for a moment. Where would 46 go? How about a 60? 60 is way off the charts up here. So whatever you thought here, I'm going to say 46 is about, I don't know, 420. Again, you can have a different number here and still be correct as long as you're kind of in this region. For the 60 inch, it's way up here, so it completely depends on how far up it goes. So maybe 700, I don't know. Like you could have had something completely different there as long as it's somewhere above like the 600-ish range. So now what's happening here is, again, these don't follow a perfect line, but they kind of go in a line-ish shape. This is called correlation. So correlation can have positive, negative, or no correlation depending on your data. If your Y values increase as your X values increase, so as X goes up, Y goes up, your values look like this, and this is going to be a positive correlation. And I always think of slope. The line here would have a positive slope, so it's a positive correlation. Whereas this next one says the Y values decrease as the X values increase. So you start high and you go low. So your Y values are going down as your X values are going up. So looking at this, this is a negative correlation. And again, think about slope. This would be a negative slope because your line is going down from left to right. And sometimes we try to make things have correlations when they actually don't. So if you have data that's spread all about here, you can't just draw a line through it and say, hey, there's a positive correlation. No, if things are spread out like that, there's going to be no correlation. Okay, so some things just have no business being together, like the temperature outside and the height of all of the students in class. Like those just don't go together. So looking at these ones, you can see A, B, and C represent each of those. So for A, you can see that looking at this, they tend to increase both your X and Y value. These would have a positive slope, so therefore it's a positive correlation. The the next one, you notice that these ones all tend to kind of decrease there. This would be a negative correlation. And for the last one, they're all over the place. I can't really draw a line that goes through a lot of the different data and accurately depicts it. This would be no correlation. Okay, let's go ahead and take a look at data that's not already graphed for us. So we want to take a look at number 2. We can see all of our different data points. So we can just do a rough sketch. 3, 4, 5, 3, 4, 5, 6, 7, 8. Okay, so 2 comma 4 is approximately there. 3 comma 5, 4 comma 7, 5 comma 7, and 6 comma 8. If you don't have your data points graphed, if they're given to you in a table, we can graph them and all of a sudden see that yes, these actually do follow a positive correlation. They also look like a line. So with that, what we're going to do is we're going to start taking things that are correlated either positively or negatively, and we're going to start drawing a line through them. This line that goes through the data is called a trend line. It's trying to show kind of the average growth or decline in your data. So looking at this next one, we can see that yes, this is correlated. They kind of follow a pattern here. And looking at this, they kind of go up both your x and your y values. So yes, this looks like a linear correlation and it is a positive correlation. And so therefore we can say that hours after sunrise increases as the temperature increases. So we can take and draw our trend line in here. And honestly, all of these are going to be different. What I normally do is I take either my pencil or a ruler and I kind of lay it on my paper and I kind of try to make it go through the middlemost of my data as I can. So I try all of these different angles and I find the one that looks to me to go through the middlemost of my data. So honestly, everyone's trend line is going to be different. This is what mine kind of looks like because I have about the same amount above my trend line that I do below the trend line in talking about data points. So an important thing to note is that everyone's work is going to be completely different because when you calculate the trend line by hand, which is what we're doing, you are going to have many possible trend lines. So your trend line is going to be different than my trend line, and therefore my equation is going to look different than yours, and that is totally fine. Especially when we get to data that looks like this next one here. So we have all of these hybrid cars in the years starting since 2000. So that's an important thing to note is it says years since 2000, which means 0 here is the year 2000. And 4 years later would be 2004. Okay, so we're looking at how many years has it been since 2000. These are also then the number of cars in thousands. We are going to sketch a trend line and then write the equation of that trend line. So looking at this, everyone should have a different trend line. Draw the trend line that you think best depicts the data. Mine is going to go somewhat like this because to me, I have a couple of points above, a couple of points below. I'm trying to go through the middlemost data that I can. Okay? So take your trend line, which probably looks different than me, and what we're going to use is we're going to pick 2 points that look nice on your trend line. So to me, mine looks like it goes through 4 comma 100. And then I'm going to pick another nice point over here, 12 comma 400. Now what we're going to do is we're going to take our points and whatever your points you have, we're going to write the equation of that trend line and we're going to write it in slope-intercept form. So to write things in slope-intercept form, we're going to go ahead and start off by finding our slope. So y2 minus y1 over x2 minus x1, we would get 300 over 8, which reduces by a factor of 4 to get 75 halves. That is my slope. Now your slope could be completely different. It all depends on your points. So as long as your slope is positive and it's increasing at a rapid rate between like 20 and 60 or something like that, you should be okay. Okay? Now what we're going to do is we're going to pick either point, and to me it really doesn't matter. I'm going to use 4 comma 100 just because. And I'm going to do y minus y1 equals m times x minus x1. And I'm going to distribute my slope to get 75 over 2x minus 150 when I do 75 times 4 and divide by 2. And then I'm going to move the 100 to the other side to get 75 halves x minus 50. So looking at this, my y-intercept does look like it would probably hit down there, which wouldn't necessarily mean that the context would start at 0. The context for mine might start maybe at 1 or something like that. Okay? So this is the equation of my trend line. Again, you could have a very different trend line depending on your data and your line. Let's go ahead and try another one now. So we're going to go ahead and take a look at the amount of time it takes to download a file. So looking at these, we have our x values and our y values. So the kilobytes here, this is going to be our x values, and the time to load is going to be our y values. And so look down here, we're going to go ahead and write internet speed. We're going to make sure it's labeled. On your y values, you're going to write time to download. And I guess we should label this as in minutes, and then this is kilobytes per second. So what I'm going to ask you to do is go ahead and graph all of these points on your graph grid. And you can pause the video and do so because I'm going to do the same, okay? So graph all of these points. Okay, here's my scatter plot. It is all of my points that I've been given for my data. We're going to go ahead and sketch our trend line. And again, you might have a very different trend line than me depending on how you see the data. So mine looks something somewhat like this. The data for me seems to have a negative correlation because they are approximately linear and they're going in the negative trend. So now what we're going to do is we're going to pick points that look like they lie on our trend line. And we're going to try and pick kind of nicer-ish points. So like this one right here, I'm going to use 54, comma 4. And then, oh, I don't see another nice one. I can kind of approximate this one, 30, comma 8. And again, yours could look drastically different depending on your trend line. We're going to go ahead and find our slope by doing y2 minus y1 over x2 minus x1. So we get 4 over negative 24, which is negative 1, 6. Now that we have our slope, we're going to go ahead and pick a point. I'm going to go ahead and use 30, comma 8. And we're going to do our equation in point slope form to get it into slope intercept. So y minus y1 equals m times x minus x1. So we get y minus 8 equals negative 1, 6, x. And then this negative times a negative becomes a plus, and 30 divided by 6 becomes 5. So I'm going to add 8 to the other side, so I get y equals negative 1, 6, x plus 13. And again, you might have a very different trend line for your data. Your slope should be negative, and it should be decreasing at a slow rate. So your slope shouldn't be anything like negative 2. It should be some sort of a fraction, and then your y-intercept should be somewhere, like looking at your graph, somewhere probably above 10. Okay? So now we want to use the equation to answer the question. So we need to go back and identify what the original question was. So our original question is asking how long would it take to download a 100 megabit file if the internet speed is 75 kilobytes per second. So the 100 megabytes is just the kind of context. All of this was time to download the 100 megabytes. So we're not going to use that one. We're going to be using the 75. And since it's kilobytes per second, this is talking about your x value. So we're going to be using x is 75. And we're going to plug that in. And we're going to solve for our y value, which would be our time. So when I plug in 75 here and I type that all in, I get 0.5. So my answer would be about 1.5 minutes. And again, your answer might be different depending on your line. Thank you for listening.